Okay, we'll continue with the topics about program correctness. So today we'll get to the more concrete part. You will see some programs and then we'll try to verify its correctness. But before we do that, let me just remind you one more thing. I'll keep talking about a predicate being stronger or predicate being weaker. So again, whenever you're giving any predicate, if we can somehow show P implies Q. So we know that P is the stronger one, okay? And then Q is the weaker one, okay? Or if you want to visualize what's happening here, the stronger one is going to correspond to the smaller set, and the weaker one is going to correspond to some larger set. Okay, just make sure you understand this. It's a very quick reminder. We're going to keep referring to stronger versus weaker. Hopefully you're okay with that. Okay, so now let's talk about just correctness. This slide is simply review, and then we'll move on to the whole triple. And then we'll see how we can apply that for the various scenarios for your programs. And eventually, maybe not today, but on Thursday, we'll get into loops. That'll be the trickiest part about verifying the correctness. So correctness is really relative, meaning that if you're given implementation, you better be given some specification contracts as well. So that is why if you're programming IFO, you do have the design, the specification already. So that's the advantage. Okay, there should be a specification, and this is the whole triple that we talked about last time. Let's just review very quickly what that really means. So when we talk about whole triple, this is what you have to pay attention to. Whenever you're given any program like this, okay, like a feature. So you have the feature over here, and then every feature may have a precondition, it has a postcondition, and it has a implementation. And the implementation here is simply very simple. It's simply a single assignment. Realistically, it can be as complicated as a series of statements, and each one of them can even be a loop or nested loop, right? Realistically. So now, this is some translation I want you to be very comfortable with. So we say the precondition, usually we just use Q, is a predicates. For the postcondition, it's simply just R as a predicates. And then we have S being the implementation. The whole triple looks like this. So you got curly brackets over here, you got curly brackets over here, and then we have Q, the precondition, we got R, the postcondition, and we got S, the implementation. So now for this specific program, what we have is this. We got I larger than 3 being the precondition. If the precondition is satisfied, we are going to go ahead and try to execute the implementation part. In this case, it's a single assignment. And then on the termination of the implementation, we are hoping that the postcondition, in this case, I larger than 13 will be established. Okay, that's what we hope. Okay. So now, one thing to note, it is really important to remember. Whenever you specify a whole triple like this, okay, this itself is really a predicates, which means you can either to prove that it is true, or you can give counterexample to show that under circumstances, there might be some false values. Okay, that's what we'll keep seeing today. Okay, it's a predicate. It can either be true or false, okay, basically, or in general, not true. Okay, any questions about the syntax? Okay, that's pretty good. So you can do the similar translation like for this program over here. Okay, now let's go on with that. Okay, so what we'll do is about whole logic. Okay, so let's just again just review the meaning for the whole triple. It is so-called a correctness predicates for your program. So you got precondition, you got postcondition, you got the implementation. Okay, and then it will be true. The whole predicate over here will be true if the implementation starts executing a state that satisfies the precondition, and then it will actually terminate. Okay, first of all, termination is one concern. Once it terminates, it will establish the postcondition. So there are two concerns over here. A is about termination. B is assuming that it terminates, it's going to establish the postcondition. So we got two concerns over here. Okay, and the first concern about termination, and the second one, okay, let me just define some terms over here. And the second one to say we assume it is going to terminate. However, termination has to be proved separately. For B here, we just call it partial correctness, which means it's not complete correctness, just partial. What's lacking here for B? Termination. So you're going to prove that separately. So if you combine A and B together, we call that total correctness. Okay, total correctness has two parts. One is about termination, and the second part is about simply assuming that it's going to terminate and it's going to establish the postcondition. Okay, that's some terminology to keep in mind. Okay. Okay, so now let's just do a little bit warm up, just get some intuition about the Hoare triple. You know that Q is the precondition, R is the postcondition. Let's think about different extreme cases to get a feel about what it means to have the pre and post conditions in this case. Okay, let's say precondition, postcondition, and implementation. What about this? What does that mean to you? Let's say this Hoare triple here. So do you think the clients might very prefer this program here or the supplier for this? The client, right? That means for me as a client, it doesn't matter what I put over there. The precondition will always be satisfied. On the other hand, supplier should be very worried. That means for the input value I get, I can assume nothing, right? Everything is possible. Okay, good. Okay, that's very user-friendly. Okay, and what about this? Well, kind of opposite, right? In this case, that means none of the, doesn't matter what you pass as input for the user, they will just be rejected. So they'll be very upset about this. On the other hand, for the supplier, it's easy because they don't have to do anything, right? Okay, all the inputs are invalid. And what about this? So maybe some precondition Q, that's not true or false. And the post condition is actually true. In this case, who should be more worried? The clients, right? Because doesn't matter what the output values are, it will just be true always. Okay, so the post condition will never be violated. So that will be very easy for the supplier. Doesn't matter what I output, doesn't matter. Okay, all the output values are valid, and then but really risky for the clients. Okay, what about this? Well, who should be very worried in this case? Well, in some way both, yeah, but who should be immediately worried? For supplier, right? For me as a supplier, I know that no matter what I do, even if I can give you like a big O of n sorting algorithm, it's not possible, of course. If I can give that to you, even that, it was to be false, right? Extreme case. So that's not good, okay? Okay, finally, how about that? If I got true and true. Basically, well, anybody want to speak up to this point of the course? If you got precondition being true, that means you have no precondition. Also, you got postcondition true, that means you have no postcondition. There's basically no precondition, no postcondition, but only implementation. So what does that mean? Well, you know, in some way, that's the working environment you're very familiar with. That's exactly how you started with this course. Because when you were in 2030, well, when you were in 2011, this is kind of the environments you're working with. You just go directly into the code without worrying too much about the precondition and postcondition. Nothing wrong with that. You can certainly still dive into the code beyond this course. But since we learned about really specifying the obligation benefits between the clients and the supplier, that's something I would hope that you can carry forward, at least in your mind. Always think about what's the precondition, what's the postcondition. This one here, nothing wrong, but it's just unconstrained on both sides. But you do want to specify clearly the relationship between client and supplier. Okay, so this one here, basically just with no contracts. It's as if you were programming in Java, in iPhone, basically. Okay, just no contracts. Okay, so now, how do we prove the Hoare logic? Oh, here comes the tricky part, okay? So we're gonna talk about principle, and then we'll talk about overall picture, and then we talk about how you can handle each scenario for the implementation. Okay, let's go step by step. So this is the predicates I have over here. Okay, let me just explain that in just for you. Okay, so now let's have a look at this. When I am given a Hoare triple like this, I got precondition, I got postcondition, and I got the implementation. I'm saying that, I'm claiming that this entire predicate will be true, meaning that the program I'm given is correct, if and only if the following implication holds. Let's try to understand that and then I'll explain to you, okay? That means Q, the precondition, is somehow stronger or no weaker than something called WP. Okay, I'll explain what the WP is. And the WP is calculated based on two things, the implementation and the postcondition. Okay, that's what how it reads. Okay, so this is the most important formula you have to know for the exam. Okay, most important. But we'll do lots of exercises throughout the lecture today and Thursday. Okay, let's try to understand what's really this. Okay, what I would do is let's just read it through. Let's WPSR is the weakest precondition for S to establish R. Okay, does this English make sense to you? Okay, what that means is WP somehow is calculated, but I will show you exactly how to calculate. So assume you're given that. Okay, if you're given WP, that simply means if your actual precondition Q is no weaker than the weakest, that for you to establish the postcondition R, you're safe. If somehow your precondition is actually weaker than that, then you're in trouble. Okay, let's see what example. Okay, I'll show you example. Let's learn from the example. Okay, what I will do is I'll show you conceptually what this is what it means. Okay, let's again look at this formula here, and then I'll show you two examples. Okay, one would be when the program is not correct. The other one is the program is incorrect. Let's look at the general principle over here. So that means we are given the precondition here, we got a postcondition over here, and then we got the implementation over here. We're saying that this entire predicates will be true if and only if, so that's equivalence. The actual precondition Q implies, which means no weaker than, okay? No weaker than the WP. For now, just assume WP is simply given. We'll learn how to calculate it in just a moment. And the WP will be calculated based on the implementation and the postcondition. Okay, this is how you can understand it. This is how the thinking process can go. Let's say R is the postcondition that we are hoping for. Let's say we want an array to be sorted, for example. That's a postcondition. And then, given the postcondition over here, and also given the implementation from the supplier, so given these two information, given these two, there is a mechanical way to calculate the weakest precondition. In this case, it's going to be exactly this circle over here, the predicates. Okay, again, let me just say again. So given the implementation, given the goal that you would like to establish upon the termination for the implementation, you would like to establish this. And now, by some kind of calculation, you can know this particular predicate over here, which is so-called the weakest precondition. Okay? This particular weakest precondition tells you any input value that will satisfy this particular set is going to guarantee, if you start from those values and apply this particular implementation, it's guaranteed you will establish the postcondition. Okay, that's the weakest precondition. Now, the question is, you don't necessarily have to always take the weakest precondition as the actual precondition. You don't have to. Okay? So now, the actual precondition you have would be okay as long as it is no weaker than the weakest precondition. In this case, conceptually, you can think about this, the green part over here. Let me say this. So the green one over here, you can see conceptually, as long as Q is somehow stronger or equal to the weakest precondition, you're okay. That means your program is correct. Okay. Guys, are we okay with this conceptual idea? Any questions? But we'll see example. Yes, go ahead.
Professor, so how do we precondition? Do you mean like it's like true? Like if it's true, then how is Q ever going to be?
Okay. When we talk about weakest precondition, we don't talk about the absolute weakest. The absolute weakest predicate will be true. Okay. However, the weakest precondition over here, it depends on two things. So it's relative. So when we talk about this calculation here, the WP, which will show you how to calculate, it depends on which implementation you're talking about and which postcondition you're talking about. It depends on these two things. So given a particular postcondition, given a particular strategy of implementation, we can calculate backwards what would be the weakest precondition for you to start with. And the actual precondition for you to start with can just be stronger than that, but no weaker than that. Okay? Let's see examples, okay, before you ask further question. Let's see scenario number one, where the program is actually correct. Okay? Let's see the example one we did last time. Okay? So now let's just fill in the information here. Okay? Let's go very slowly. Okay? Now, we know that First of all, let's go the order I just suggested. Let's start with pink. So this is the post condition we have. So I'm going to put I larger than 13. That's a post condition, right? And then the blue one is going to be the implementation. So the implementation will be I is assigned to I plus 9. Okay? For now, simply assume you're given the weakest precondition. I'll show you how to calculate. Let's say the weakest precondition is simply just I is larger than 4. Just that. That's the weakest one, which means your actual precondition can only be stronger than that, but not weaker than that. So that means in this case over here, let's see, what's the actual precondition over here? The actual precondition is actually I larger than 3. And we know that I larger than 3 is actually weaker than the weakest precondition. So that means this program is not correct, conceptually. More specifically, how we disprove the correctness of this program is we simply show a value, for example, 4. When I is equal to 4, in this case, when I is equal to 4, it's going to satisfy the precondition, and then I is simply going to be 4 plus 9, which is 13. But 13 larger than 13 is not going to give you a satisfying postcondition. So that's how we prove that the postcondition, this program is not correct. But conceptually, that's how it works. Oh yeah, you can definitely use other things, but let's focus on this particular example. Yeah, but we'll see something, and we'll see another program that will be correct. So hopefully that will answer your questions. Okay, guys, are we okay with this illustration here? So you can see that what's really left unknown is how you calculate the WP, which we'll see. That's really important.
Professor, just one quick question. In this illustration, we see that weak precondition is inside Q, but in the other illustration.
Yeah, exactly. When we talk about another illustration, we'll see that in just a moment. Okay. Yeah. So first of all, we can see that the actual precondition, which is green, is actually weaker than the orange one, which is the weakest precondition. So that's how we judge. This is not correct. Okay? Now, okay, yep. Let's go to the other example over here. It's going to be the opposite story. Let's do it again, okay? Now, again, let's go slowly, just in the right order. We're given a particular postcondition over here, which is I larger than 13. And then we're given a particular implementation strategy over here, which is I is assigned to I plus 9, okay? And then we can calculate the weakest precondition. Let's say for now, we know that already. It's going to be simply just I is larger than 4, okay? And the actual precondition we have is I larger than 5. And we agree that I larger than 5 is no weaker than that, no weaker, which means it's stronger, okay? So this is correct, okay? What we have justified so far is simply informal, because we don't know yet how to calculate the WP, okay? But you have to know how to calculate that, okay? Basically, what you will be given in the exam, you will be given a program like this. Possibly the postcondition and precondition will be a little bit more complicated, and also implementation might contain a loop. And then I'll simply ask you a simple question. Prove or disapprove if this program is correct. And what you gotta do, number one, you gotta calculate the weakest precondition. And then you want to judge to see if the precondition given implies the WP you just calculate. That's going to be exactly the process you're going to go over. Okay? Questions? Yeah.
Isn't this precondition too strong?
Oh, yeah. So this precondition is definitely stronger than the weakest precondition. That's okay. In practice, you don't necessarily always have to choose the weakest precondition for the precondition. You don't have to. As long as you choose something that is stronger than that, of course, you might go for the extreme case, false. But that's not going to be very useful, right?
Like if I is equal to 5, it fails the precondition, so it would actually satisfy.
That's okay. So, okay, good question. So we talk about two concerns over here. One is about whether the program is correct or not in the first place. And the second is, given that the program is correct, what should be the appropriate precondition? In which case, it will be your judgment as a supplier. And there should be some mutual agreement between you and the clients, okay? So again, what I meant is, when we calculate this particular weakest precondition over here, it's completely objective. It's just be about, given this and given that, what should be the weakest one? And then go to the second issue. For me as a supplier or clients, how should we agree on an appropriate precondition? An appropriate precondition should be anything as long as it is stronger than or equal to the weakest precondition. What that should be is completely up to the design. Okay? So I will only ask you about whether the precondition, whether the program is correct or not. I wouldn't ask you whether it's a good design for the precondition, right? It's a different issue here. Guys, any questions? Hopefully the big picture is clear. Okay? Yeah.
Professor, can you the case that true turns out false as precondition and you still get the the end result as true?
Oh, absolutely. Of course, the extreme case can be. Absolutely. I think one of the examples I will show it to you. In the extreme case, let's say simply for this Q over here, I simply choose Q to be false. And we know that false implies anything. That means it doesn't matter what the weakest precondition can be. False over here always implies that. That's true. The program itself will be correct. Now let's go to the second issue. Is it an appropriate design? Maybe not, because if you have the precondition being false, that means it's extremely user unfriendly. Your clients will be very upset, even though the program is correct. Right? Guys, are we okay? Yep. Let me say one more thing, since we mentioned that. Remember the several scenarios that we talked about before? I will just mention this very briefly, but you can think about it when you review the lecture. When you look at this particular one, we got true being the precondition, and we got true being the postcondition. Once we learned about everything at the end of the lecture, you can justify by yourself. When we have the pre and postcondition both being true, the program is always correct, which means it doesn't matter what you put in S, because you are completely unconstrained on the input and output. Of course, it is correct. Again, correctness is a very relative notion. If without some very complete and appropriate pre and post condition, this is really hard for you to judge if things are correct or not, or even appropriate. Okay. All right, that's good. So these are the two examples, and then let's go on. Okay, so what I would do is, so now how do we calculate the weakest precondition? The Q and R are simply just predicates. That's something we are very familiar with. Now, how do we, there are many different cases for S, the implementation. So S can be assignments, which we'll do right away. Okay, assignment is the simplest case, or it can be alternation or conditionals, if then else, or it can be sequential composition. In the case of Java, you simply got semicolon, where you want to say do this, and after that, do another thing. In Python, simply hit enter, just new line. Okay. And then loop will be something we'll focus on Thursday, okay? And we have loop. And also for those of you who are learning 3101, you learn about looping variants, right? We'll see how the looping variant will work in the programming context. Hopefully that will strengthen your understanding as well, okay? And now we'll learn about how to calculate WP, okay? That's the issue. Okay, so this basically just a repetition of what I just said in the iPad. So if you consider the two examples, you will see that a precondition that is equal to or stronger than the WP will result in a correct program, right? That's basically this case over here, right? On the other hand, if you got a precondition that's weaker than the weakest precondition, that would be this case. So that means the program is not correct, okay? So these are the two cases that we just talked about. So we can go over the slides. Okay, one more thing, one more slide to mention, just some convention over here about denoting the values, and then we can talk about the rules for WP. We'll talk about 3 today, okay? So in the post conditions, so whenever you talk about any variable, let's say x, balance, or count, okay? In the pre-state, remember we're talking about pre-state versus post-state, right? Pre-state simply means before the execution of the body of the feature, right? Sometimes we may simply have a subscript 0. To say x0 simply means the value for x before the feature is executed. Okay, you will see that. Okay, just and also if you have no subscript 0, that means that's a post-state value. Okay, so x0 versus x, they denote the same value, but they denote the values either in the pre-states or post-states. Okay. Okay, and now for example, you can see that over here we say that b0 larger than a, for example. Right, we're saying that the pre-state value for b should be larger than a, and then in the programming text, we simply b is assigned to b minus a. In the post condition, this is what we say. We say the post state value for B is equal to B0 minus A. You can think about 0 as like an odd in iPhone. Okay? Okay, good. That's about the convention. Okay? And just one thing, well, for these two remarks, we'll actually go over them as we learn about the rules. So you can go over them on the slides by yourself. Okay? Okay, number one. So now we're going to talk about 3 WP rules. We'll do assignments, we'll do conditionals, and we'll do sequential composition. Okay? Let's do the first one. And once we learn about the first one, we can solve the examples 1 and 2 already. Okay? Let's say this. So let's try to, again, read this particular one very carefully. What we are trying to do here. WP, you can think about WP is simply just a function. And the function takes 2 inputs. The first input is simply a programming statement, like an implementation. Okay? X is assigned to E. And then the second argument there is simply just a post condition, some predicates. Okay? And then the output for this function here, WP, is simply just a Boolean, just a predicates, either true or false, or something like that. Okay, let's learn about the definition here. The definition simply say, given a post condition, what would be the weakest precondition for you to establish R by executing X is assigned to E? Okay? The definition is you simply take R as is, replace every occurrence of X by E. That's what it is saying. But we're going to see exactly how you can apply that. Okay? So now, given this, let's apply right away. Okay? Let's go on to example number 1. Okay? Let me just write it down to remind you what the rule is. So we have WP. So X is assigned to E. In this case, let me just put it right away. In this case, let's say the implementation is over here. I is assigned to I plus 9. I is assigned to I plus 9. That's the first input for the WP. And the second input is simply the post condition. I is larger than 13. Okay? How do we calculate that? Okay? So now, this is the kind of style I will hope that you will pick up, okay, for the exam. Okay? Whenever you want to say any equal sign, you want to justify why that step should be the case. Okay? This is the format you can pick up. So now the equal sign over here, I'm just going to have some brackets over here, and then I'm going to say whatever value I put over here can be explained by this particular step. Okay? So what I will do is I'll simply say by the rule of WP for assignments. Okay? You will see that in the slides I follow these styles consistently throughout. So now, by that, I'll simply say, remember what we have is this. Just repeat the predicates, the post condition, and then try to replace every occurrence of X by E. Okay? What I mean by that, I'll do one more step. I will say I larger than 13, which is the post condition over here, and then I would say replace every occurrence of I by I plus 9. Okay? And I'm running out of space, but I'll just say equals over here. Okay? Basically, what I would do is, let's say this. Every occurrence of I, for example, this is one occurrence of I. Replace that by I plus 9. Replace that by I plus 9. What I have is I plus 9 larger than 13. Let's simplify that. That's simply I larger than 4. And no magic. That's exactly the weakest precondition I gave to you. Intuitively, does that make sense to you? Do you have this? Think about what we're doing here, okay? Think about it. Let's say this. Okay, just explain for the first one. What we really want in the post states is to say I is going to be larger than 13. So the I that we talk about over here is the post state value for I, okay? But how do we actually get to this particular post state value for I? The way we get there is by substituting I by I larger than 9, because we're doing this particular assignments over here, right? So whenever you talk about I in the post states, it is equivalent to I plus 9 from the pre-states. Okay, so that's why you can go backwards to get the weakest precondition. Guys, any question about this? Yes?
What if we ask if the R is not free?
Good question. Yeah, good question. When you see the question was, what if the value for I or X is not free? So it's really important. I'll give you one, okay, let's say this. So here you can see all the free occurrences of variable x in the postcondition R by expression E, right? So the free occurrence is really important, okay? So I'll give you one example. Let's see. Let's say this. Let's say I simply got, let's say WP, okay? Again, I have, let's say x is assigned to x plus 1, okay? And then over here, the postcondition, I'm going to put in the second line. So what I would do is I'll simply say, okay, this one may be a little bit complicated for now, but I'll just want to illustrate to you. Let's say sigma x, you know what a sigma is, right? 1 until 10, and then I will simply say x. Okay, I'm just basically sum up 1 to 10. Okay, and then plus x is larger than 10, for example. So basically, this thing over here is the postcondition. Okay, if you look at that, so now we got 2x over here, right? So now which x is free? The second one, right? Okay. Free simply means it's not really bounded by any quantifier. And quantifier can be universal quantification, it can be existential quantification, or it can be any summation symbol. Those are the common ones. Okay? So in this case, we'll simply get x is the free. And this x over here is bounded to this particular one, is bounded. So when you actually want to get this weakest precondition, what you would do is, let me illustrate this. So you know that you have to replace every free occurrence of x by x plus 1. So I only need to replace this particular free occurrence of x by x plus 1. But for this x, I can leave it the same. Because back in 1019 or 1090, you learned about the dummy variable for the quantification can be renamed consistently to y or to z, right? Okay, that's something I just wouldn't touch, right? I assume you know that already. But I would say typically the example we had to deal with, you don't have to worry too much about the free occurrences, but you have to be aware of. They might be there in some rare cases. Okay. Guys, are we okay with the assignments? Okay. Let's do examples together. Okay. So that's about the first rule. Okay. But I would say the first rule is really very concrete. You are just saying you're assigning a value to something else. That's why you can just do a substitution. Okay, so now, remember we said before, if we got a whole triple, it will be true because of the correctness predicates. It will be true if and only if the actual precondition implies the weakest precondition, right? So now here is my question for you. If I'm given a program like this, having precondition Q, having postcondition R, and the implementation is simply x is assigned to E, how do I express another predicate to prove that this is true? What should I prove? According to what we just learned, we want to say Q implies the weakest precondition for x is assigned to E to establish R, right? That's something we want to say, okay? So there are two things you want to bear in mind. In order to answer this question over here, so this principle here is always applies. In order to prove that a particular whole triple is correct, you want to make sure the actual precondition implies the weakest precondition, right? But now we talk about the weakest precondition for assignment specifically. So what you would get is something like this. The actual precondition implies the weakest precondition for assignment, which is taking the postcondition, replace every occurrence of x by E. Okay? Guys, is that clear? That's just a rule, okay? Okay, that's about the assignments. And then let's do some example together, okay? Okay, let's see what I have over here. Okay, good. What I will do is, let's do this one here. Now, why don't we try this all together, okay? Now, here's a question. I'm not really asking you about the correctness. Let's leave that for once we introduce the next rule. For this, we want to be simple. If given some program, x is assigned to x plus 1, And then I want to know what is the weakest precondition for this implementation here to establish the postcondition x is larger than x0. You can see I'm using x0 here. It is as if I say x is larger than OX. Okay? Calculate in your mind what should be the weakest precondition. If you can, tell me the answer. Otherwise, we can do it together. Okay? I'm going to write it down on the iPad. Give me one moment. I'm just going to copy that down to iPad, and then we do it all together. You know, before we try to do the mechanical calculation, let's get some intuition over here. Okay? Now, what's really being asked over here? You're saying that what I really want to achieve is the new value for x is larger than the old value of x. That means x has been incremented. Agree? And now we are saying that the implementation I gave to you simply will just increment x. So that means this will just work no matter what. Does it really matter what x is in this case? If x is negative, let's say, if you try to plus 1 to a negative number, you definitely get a larger number. If you try to get plus 1 to a 0, that will also give you a larger number. If you try to do plus 1 to a positive number, that will also give you a larger number. That means the precondition doesn't really quite matter, which means it should be just equivalent to true, intuitively. But you cannot just say this intuition on the exam. You have to prove it. Okay? Let's see how we can prove it. What about I just give you, how about, this is only our first example. Let's get used to the format. Let's do it together. So what we really want to do is we want to calculate the weakest precondition for this particular implementation to establish this particular postcondition. Okay? Very easy. So we say it's going to be equal to, and based on the WP rule for assignments. Okay, just call it equal. Okay? So what should we do? We should simply say x larger than x0, and then we're going to replace every occurrence of x by x plus 1. Like that. Now, I have a question for you. So now this is something we have to decide. So we can see that we have x, we got x0 over here, right? So this x basically is the post-state value. And this x0 here is the pre-state value. Agree? Okay, that's a postcondition. And now, before we do the replacement, when I talk about this x over here, am I talking about a post-state or pre-states? Post-state, right? That I'm saying in the post-state, I want x to be assigned to whatever value it is. So we are really talking about the post-states. That means every occurrence of x should be replaced by whatever this is, right? Now x over here, is that a pre-state or post-states? Pre-state or post-state? Pre-state, right? Because in this case, we're saying that whatever x value is, x plus 1 is going to be assigned to x to become a new x. Okay, that's something you want to get. So this is as if we said x0. Okay, so now once we do the replacement, we're going to replace every occurrence of x by x0 plus 1. So what we will get is x0 plus 1 larger than x0. Are you okay with this? And now, can you see what that simplified into? Well, that means 1 larger than 0, right? Well, simply just true. So don't lose the big picture, right? What we have done is, in order for this particular implementation to establish the postcondition over here, the weakest precondition will be just true, which means any input value that will satisfy true can guarantee such satisfaction of the postcondition by this particular implementation. Now, is there any input value that's not going to satisfy true? No, because true is simply the weakest one, right? Okay, that's true. Now, that's the first issue about correctness. In order for this particular program to be correct, you can choose anything that is stronger than that. Okay? So issue number 1. To be correct, choose any precondition Q that is stronger than true? Well, for example, it could be, you can say x larger than 0. I'm saying that x must be positive. That will work. I can say x should be just 0. I can say x should just be negative. Or I can say it should just be false. That's also fine, as far as correctness is concerned. Okay, that's issue number 1. And then, to be appropriate design. So this is something you as a designer should judge. Okay, it's up to the agreements between the clients and supplier. For example, if you simply choose false, even though it is correct, but client may not be so happy because that means none of the value you can pass for the input for this particular feature. Okay, are we okay with this first example? So I think the purpose for this first example here is for you to get used to how to calculate WP. All right. Okay, that's about this. Okay, so that would be finally true. That means any precondition is okay. But false, for example, it may not be so useful. Okay. Okay, for this one here, why don't we just calculate in our mind? Hopefully you are very used to assignment, which is very easy. Let's say we got the same implementation. Sorry, not this one here. How about this one here? You know what? I think I should really change this. It's a typo. It should be x equals 23. Okay? So look at the whole predicate over there. So I'm asking the following question here. If the implementation is x plus 1, and then the postcondition I would like to establish would be x is equal to 23, what should be the weakest precondition? Huh? Anybody? X equal to 22, right? You simply substitute x by x plus 1. That means you got x plus 1 equals 23. So you got x equals 22. So that is the weakest one. Okay? So the weakest precondition for this would be just x equals 22. Okay? Let's agree on that. So now, if I choose, let's say, x larger than or equal to 0 as the precondition, can the program be correct? No, because x larger than or equal to 0 is a strictly larger set than just x equal to 22, right? So that's kind of the idea. Yeah. Yeah.
For the weakest precondition, it has to be x0 equals to, not x equals to.
Yeah, over here you can see x0 here simply tells you that in the pre-states. But it depends on the context. I would say we are not so strict on this. Sometimes if you say x0, we know what you mean. But when you have to distinguish between the pre and post, you better put 0 there. Yes?
Sorry, this is supposed to be, the post condition is x is greater than 23?
You mean the post condition? Or, yeah, over here the post condition is simply x equals 23.
Okay, so then x equals to 22 is the weakest precondition and the only precondition, right?
Well, in this case, yes, that's the only one. But x equal to 22 is also like a set. It's a singleton set. You can think about in this case, yeah. Okay, in this case, when we have actually got WP for x is assigned to x plus 1, and then you got x equals 23. So the calculation we get is x is equal to 22, right? So now you can think about it's also like a set. It's only a singleton set, which means only 22 can be there. Anything that is not, anything that's weaker than that is going to be, it's not going to be good. It's not going to be correct, right? For example, you might say x larger than or equal to 22, right? It's going to be something strictly larger, but it includes, for example, 23. That is not going to work, right? Good. Very good. Guys, any question about assignments here before we move on to something that's more interesting? Okay. Okay, that's about the assignments. So let's talk about if then else. Okay, if then else is really interesting. Okay, before I show it to you, okay, let's try to think aloud. Okay, because I do want to give you the idea about if you forget, there's one particular connector that's very confusing. I'll use one example to justify to you. So in case you forget in the exam, you can reproduce the process. Okay, basically, you know what? Let me just create a new page over there, and then we'll talk about it. Okay, let's talk about the weakest precondition for alternation, or conditionals. Okay, I want to know WP for if B, a Boolean expression is true, and then I will do certain statements just S1. S1 can be assignment, for example, in this case, right? But we'll see concrete example in just one moment. And if B is true, I do S1. Otherwise, I will do S2. That's why it's called alternation, either way. And I would like to establish R. Okay? Now we want to figure out what's the weakest precondition for this one here. You can see apparently this is more complicated than before. Because when you do the assignment, you always just do the assignments. But now when you run an alternation, you only go one of the two branches, right? It depends which one you go. Okay? Let's now be a little bit more logical here. If I happen to do S1, what can I assume? If I happen to do S1, that means B was true, right? If I could do S1, okay? If I happen to do S2, what does that mean? B is not true, not B. Okay, start with this. Okay, everybody's comfortable with that. So now, let's not worry about combining these two branches together just yet. Let's do each branch separately. Okay, branch number one. If I'm in branch number one, that means I'm going to execute S1, and then I'm hoping that I can establish R. It's one of the branches, right? So now, basically, I want to say, I'll put it down here. What I would do is, I would say somehow the WP for me to establish R by executing the first branch, which is S1. However, for this particular WP, I am assuming that this particular B is true. So I'll say if B is true, and then I can say this particular WP should be the case. If B is not true, I don't care about this. Okay? Are we okay with this? Okay, let me just finish this, and then we'll discuss. Okay? Now, let's apply the same logic. Okay? If I try to apply the same logic over here, it's like this. If I happen to execute S2, in that case, I want to know what is the weakest precondition for S2 upon termination to establish R. And because I'm now in S2, I can assume something more, which means outside this assumption, I simply don't care, right? That means not B. Okay? Are we okay with separation of concern? Okay? Now, here's a question. Okay? If you simply say the WP for an alternation is simply these two, that's simply wrong. It's not type correct. Because the result for WP should be a single predicate. But now we got two predicates over here. That's not type correct. Somehow we want to combine these two predicates together using one of the logical connectors. How many binary logical connectors do we have? Well, we got conjunction, we got disjunction, also we got implication. Right? Based on your project, you should know this very well, right? Okay. Let's not worry about implication. I can tell you implication is not the case here. Okay? Now, by your intuition, okay, so that, okay, everybody comfortable with so far? Okay? We got choices. Either we can combine the two using disjunction, or we can combine the two using conjunction. Intuitively, which one makes more sense to you, the blue one or the green one, intuitively? Green one? Okay. Blue or green? It's okay. It's okay to be wrong. You're excused to be wrong because I haven't told you how to justify that. I want to know your intuition. What I hope to have is everybody's intuition is wrong. That's what I hope. So that means math is really helpful, right? you can work backwards, right? Okay, good. Blue, green? It should be exactly one of them. Exactly one of them. Yeah, we'll see the example in just a moment. Shall we do a vote? Blue? Okay. Green? Green seem to be the minority. But unfortunately, green is the one. Yeah. Let me tell you the intuition before I go on to justify why it should be the case, okay? For the blue one, it simply says, in order for me, thinking this way, if I'm given this particular alternation over here, I want to say eventually I want to establish R, right? That's what it means. The blue one simply tells me as long as one of the branches is going to establish the postcondition, that'll be okay, as long as one of them. That's why I use conjunction over here. Okay? The green one is really saying both branches must be able to establish the postcondition. Both branches. Intuitively, actually, this should make more sense because at the runtime, you may go to either branch, right? Depending on what the value is for the variables. You might go for branch number 1, in which case you must establish the postcondition. You might also go for branch number 2, in which case you should also establish the postcondition. That's why conjunction should be the case. But this is a little bit too intuitive, too informal. Let's try this particular example over here I put in the red. Okay? Why don't we just try the case where, let's try the WP for both cases, and then we'll see whether the conjunction will work or the disjunction will work. Okay, let's do that very quickly. Okay? Let's try. Okay, what I would do is, let's say, okay, let me use a different color here. Let's say if y is larger than 0, then we will do branch number 1. Okay, the pink. If y is not larger than 0, then we will do, let's say, purple. In that case, it is x is decremented. Okay, but what we really want, oh, they look the same, right? Yeah, I lose the purpose of that. How about this? Orange. Okay, that's better. Okay, so either we go for x is incremented or x is decremented. And the postcondition is we want x to be larger than or equal to 0. Okay, what I would do is I'll highlight this particular postcondition over here. So x is larger than or equal to 0. Okay, let's try the 2WP. Okay, let's write it down. Okay, basically I'm saying the following, and then I'm going to use blue. Okay, just black. That'll be fine. So for the first, if y is larger than 0, that means I'm going for the first branch, in which case it should be the WP for the pink one over here. For x is assigned to x plus 1 to establish x larger than or equal to 0. Right? Like that. Okay? And then we also got something like this. We got if y is less than or equal to 0, the negation of that, right? Implies WP for, over here, x is assigned to x minus 1. And then establish the same postcondition. So far so good? Okay. So now let's go a little bit further. So now let's just worry about this part over here. Okay? Just this part. Oh, let me just be consistent with the color. Let's go for the pink one first. For this part here, what would that be? What's the WP? Let's practice. What would that be? X, would you agree, is x plus 1 larger than or equal to 0, right? X larger than or equal to minus 1. Everybody agree? Okay, please, if I'm wrong, let me know earlier than later. Okay? Okay, good. The second one is going to be orange. If I go for orange over here, what should that be? X greater than or equal to 1, right? Okay, now, let's just ignore this part here, just for now. Okay, just take these two to get some idea. Let's say one part is x larger than or equal to minus 1. The other part is x larger than or equal to 1. Okay, let's now go for the blue version. Okay, for the blue version, this is what we will get. For the blue version over here, we're going to get x larger than or equal to 1, or x larger than or equal to 1. Oh, sorry, negative 1. Yeah, sorry. What am I writing here? Okay? So what do we have over here? Yeah, actually, that would be x simply larger than or equal to -1, right? Okay, everybody comfortable with that? You can think about doing disjunction over here is like doing a union. So whichever set is larger, that should take one, the weaker one. So that is simply equivalent to x is larger than or equal to -1. Okay? So this is actually not very good. Can you see why over here? And let's just also calculate the right-hand side as well. Okay? Let me just put this part here in blue. Let's also try the green one. The green one is going to be x larger than or equal to -1 and x larger than or equal to 1. And in this case, it's more like doing an intersection, right? So that means it would be just equivalent to x larger than or equal to 1. That's the weakest precondition, right? Okay. So far so good? Okay. So now, what we should do now is try to apply both predicates to some value. Okay. So now, let's see what we can do. So now, in the case where it's actually simply just x larger than or equal to 1, what we really want to justify is this particular WP is too weak. It allows certain value that is going to let us get into trouble. Can you see which value it is? 0 or -1? How exactly? Anybody want to try to explain? How about just -1, let's say? What if x is -1?
If it goes into the else, you do -1 minus 1, which is -2, and that doesn't satisfy.
Exactly, very good. Let's just repeat exactly what you said. That's good. Let's try to follow this. So this particular weakest precondition tells us as long as x is larger than or equal to -1, it's going to establish the postcondition. But in this case, if x is simply just -1, right? In that case, if x is simply -1, so -1 minus 1 will give us -2, right? And then -2 larger than or equal to 0 will just give you false. That will violate the postcondition. Okay? Apparently, y can be any value you can just tweak to make this implication true, right? So that's why I can say we just ignore the antecedents for the implication. Okay? Guys, are we okay with this?
Oh, Professor,
Yeah.
y, the value of y here doesn't.
Well, somehow the y does not really affect what the x value is. So somehow I can simply make the value, let's say negative in this case. So negative for the y, and then for x is also -1. In that case, -1 minus 1 will give me -2. In that case, that will violate the postcondition, right? Yeah. Let me be more precise over here. So now when so what we would choose is this. So what we would choose is, for this one, choose y being -1, which will satisfy this particular antecedents, and also we will also choose x being -1. If you try that one there, it is allowed by this particular weakest precondition by using disjunction. However, for that one there, it is going to violate the postcondition eventually because we're doing decrements, right? On the other hand, if you try to use the conjunction over here, it is going to work because the -1 will simply be disallowed, right? Okay. So this part here is not something you will always think. It's only when you forget that you should use conjunction rather than disjunction. But I would say it's really good to really train your process of thinking, right? In the worst case, if you really forget whether there should be conjunction or disjunction, try to just find out this example here in your mind and try it. Okay? Guys, any question here? Yes.
Question.
Yeah.
Over here we have like 2 branches.
Yeah.
Can we do like more than 2 branches?
Absolutely, absolutely. The question is, what if we got more than 2 branches? Basically talking about if, else, right? I would say we might see some example a little bit later in the lecture, but I would say for now, let's just make it simple, just 2 branches. Yeah, yeah. Let me give you something since you asked very quickly. Very easy to generalize this very quickly. This may be something you haven't thought about, but very straightforward. Let's say this. If I say if B1, then S1, okay? Else if, of course this applies to Java as well, just syntax is different. let's say B2 over here, then S2. Otherwise, I do S3. Okay, so this is general. Okay, you can have as many else if as you like. Now, basically, let's say we started with some precondition Q, right? And we also end with some postcondition R. Okay, so now in order to calculate the weakest precondition, what we're going to have is, again, we got WP over here, and also WP for S1 to establish R, and also WP for S2 to establish R, and also WP for S3 to establish R, right? And we know that eventually we got to do conjunction. So now what's left is what antecedent should we put? And then, of course, we got implication here. Anybody want to try? What about the first one? What would be the assumption we can make if we can execute S1? B1, that's why it's easy. What about if we can execute S2? What does that mean? Aha, very good. Remember the semantics for the runtime. You can only get to B2 if B1 is actually false, right? Okay, so not B1 and B2. What about S3? Aha, you guys are following, good. Not B1 and B2. Oh no, be careful. If I say this, that's wrong, right? That's wrong, yeah, that's why I said be careful. Neither of them is true, okay? Well, of course, you can also say not B1 and not B2, right? Yeah, that actually answers your question, yeah. Well, since I talk about this, so this might be an exam, right? But I'm just saying, be careful when you calculate the branches, okay? All right. Okay, let's go on to the next one. Okay, that's exactly what I just talked about. Okay, so all branches should do. So now let's ask the same question again. Recall, this is what we said. In order to establish R by S, we just do if the precondition actually implies the weakest precondition, right? So now here's a question. How do we prove that an alternation program establish R? We have to make sure the Q here establish the weakest precondition. Sorry, let me say it again. The Q here implies the weakest precondition for this program here to establish R, right? That's what we should have. Well, you can follow the logic, but eventually this is what you will get. Okay, let's have a look at just this part here. Okay, this part. Basically, we are saying the following: branch B or branch not B, right? If we go to branch B, then we go S1. If we go to branch not B, we go to S2. And for both cases, we can also assume the precondition is true commonly. Are you guys comfortable with this? Okay. Now, I want you to make sure you really got it. Seems like you guys seems to be very strong in logic, right? Maybe, maybe not. Okay. How about this? Let me do this for you. Let's say this. If I got Q over here, and then I have if B, then S1, else S2, R. Okay, let me write it down very quickly. What we want to have is, it will be true if and only if Q implies, let's get to the form you're comfortable with, implies the following. Okay, we're going to have B implies the WP for the first branch, S1 to establish R, right? And not B, the second branch, the WP for S2 over here to establish R, all right? Now, how do we actually move Q inside, okay? Okay, that may be something you're struggling with, right? Let me give you a keyword. Let me give you a keyword, which I'm pretty sure you learned about in 1090. Have you even seen this word before, shunting? Okay, maybe you did, but you just forgot. Okay. I'm pretty sure you have seen this. I'm pretty sure. Tell me the name of your prof in your 1090. I'm gonna ask him for sure. Oh yeah, no, I'm joking. It's okay. Yeah. Yeah, no. I'm too junior to ask him actually, so I better not ask him. Okay. Okay. This is shunting. Okay? When you got P implies Q implies R, equivalent to what? P and Q implies R. At least have seen this, right? Okay, that's called shunting. Oh, really? Oh, interesting. I thought it is a standard name. Huh? Say it again? What do you mean? Induction? Reduction. Oh, I haven't heard of it, actually. Yeah, anyway, maybe right. It doesn't matter. Okay, the name is not important. Okay, basically what I'm trying to say is, based on this particular theorem, you don't have to know how to prove it. Okay, based on this, we can simply distribute Q into here and Q into here. That's what we can do. Okay, that's why you will see something like this, Q and Q here. Okay, that's something I want to mention. All right, let's do one proof quickly. Okay, how about, is this program correct or not? Okay, we start with some precondition here. X and Y are positive, strictly positive. And then the postcondition should be the bigger is larger than or equal to the smaller. Okay, and bigger and smaller, of course, they are two variables. And we're saying that if X is larger than Y, then we assign bigger to be X, smaller to be Y. Otherwise, bigger to be Y, smaller to be X. It looks dumb, but you know, let's try. Okay, yeah. I do have a challenge for you at the end. Don't worry, we'll get there. Yeah. This one, you know, I thought about just writing together with you, but it seems to be very simple. Okay. I think what's really important. Let me just write down what you need to know, and then I will leave you with the rest. Let's say you're given this in exam. Okay. There's two steps you got to do. Okay, what you have to do is like this. First of all, calculate the WP. Okay, step number one. Step number two, prove or disprove the actual precondition, which is over here, x larger than 0 and y larger than 0, which is over here, implies whatever WP you calculate from the first step. Okay? Okay with that? Okay, now, I just want to show you very quickly in the beginning step that what you should do, and the rest will be very easy. How do we calculate the WP over here? It's going to be the WP over here for the following. We say if x larger than y, and then I would say B and maybe B and S. How about that? Okay, bigger is assigned to x followed by smaller s is assigned to y. Okay, otherwise, over here, b will be assigned to y, followed by smaller will be assigned to x. Okay, and then at the end, okay, let me just say this. In the end, it's going to assign b is larger than or equal to s. Okay, so far so good. And now, let's see how we can simplify. This certainly is something you haven't learned just yet, which is sequential composition. But let's see how, to what extent we can simplify this. Okay, well, I'll change the color. So that would be equal to, so we should have a conjunction, right? If the branch is true, x larger than or equal to y implies something here, and if x is less than or equal to y, okay, or you can put it this way, if that makes more obvious to you. You can say not the case, x larger than y, okay, implies, and now, WP of what? This, yeah, this part, right? Good, the green one. Okay, I'll say the green one over here, just copy that to establish b larger than or equal to s. And then WP over here, I will make another color here. What about pink? Okay, this one here, the pink one over here, for that to establish b larger than or equal to s, right? That's as far as we can simplify into, based on what we have learned now. But now, in order to calculate the green and the pink, we have to know how we can deal with the programming construct of sequential composition. That's the next topic. Okay? Okay, so far? Okay. Guys, are we okay, right? Hopefully. Okay, now. Okay, let's go a little bit further. Okay. Now, let's go back here. Of course, you can follow that. That's exactly what I said. But now, how do we calculate sequential composition? So now, this is the final rule before the loop. Okay? How do we deal with sequential composition? So this will make your program very general. That means you can have as many alternations as you like. Inside each alternation, you can have as many assignments as you like. Okay? It can be very general. So that's why it's really important. Thinking this way, I have the following program. I want to execute S1 and then S2. Upon the termination of S2, I want to establish R. Okay? That's basically what I'm doing here. Okay? Now, let's try to see, without presenting to you the rule, let's think about how things will work. Again, I want to give you a little bit intuition about how this rule can be derived. So if I got the WP for S1 followed by S2, and then I want to establish some R. Okay? So now, the rule looks a little bit complicated. Okay? Thinking this way. All you have to think about, you got to think a little bit backwards. Think about what's going to be the last part of the program being executed. S2. Agree? It's basically like we got two phases, phase 1 and phase 2. Let's only worry about phase 2 just for now. Okay? That's going to be the last phase. So basically, we can think about for the last phase like this. Let's put S1 away just for now. Okay? That means I can calculate WP for S2 alone to establish R. Just that. Okay, so far so good. And then this WP can be treated as the postcondition for S1. Okay? So what I have is I can see what would be the weakest precondition for S1 to establish this. I'll repeat. Okay? This is how you can think of it. Okay? We're thinking this way. We got S1, we got S2. Okay? So these are the two programs. And then, so we got one state over here, we got another state over here, we got another state over here. Okay? And apparently this is the intermediate states. Okay? So now, the final state we want to establish will be just R. In order for S2 to establish R, we want to make sure the intermediate state is no weaker than the WP for S2 to establish R. Agree? And now, what should be the final precondition over here that's visible to the clients? It must be no weaker than the weakest precondition for S1 to establish this, the intermediate postcondition, right? So that means what we will have over here is, what we have here is for WP for S1 to establish this guy over here, which is the WP of S2 to establish R. Make sense to you? Of course, it looks a little bit complicated, a little bit more abstract, but we got to apply that. Okay? Let's try. How much time do we have? 5 minutes, maybe? Okay. Let me pose a challenge to you first before I try to go over the program to you. Okay? The program we want to verify altogether is something like this. Okay, of course, you can also go over this rule. It's very easy. What's this program doing? Can you at least see what it is doing? Swapping, right? So now I have a challenge for you. Let's say the post condition is we want to say x is larger than y after the swap. Okay? Now, the implementation over here is a very standard way of doing the swap. You simply want to have intermediate variable temp and do the swap. I have a challenge for you. Can you change the implementation so that you don't have any intermediate variable? You see what my question is? I want to say, we're going to prove this for sure, but here's my challenge for you. Can you give me another correct implementation so that there's no intermediate variable? No, you just need you just need x and y. Only use x and y, and you have no intermediate variable. By the way, this is an interview question I just heard from my colleague by one of the companies. That's what I heard. Can you do it? How about this? I give you pressure. try to do this within 1 minute. Let's say this is what you're given. Okay? I think it's more fun to talk about other than the one. Okay, now here's a question. As soon as I state a question, you have 1 minute. Swap x and y without using a temporary variable. Okay, I'll just give 1 minute to everybody. Okay, it took me 2 minutes. I should give you 2. Think about it. Let's take 2 minutes, okay? And then we'll finalize the implementation here, and then we'll do the proof on Thursday, okay, quickly. So that means you got one proof that's on the slides, another proof that's going to be something we come up with all together. That will be an exercise for you. No intermediate variable. How would you do it? Guys, I didn't make this up. It's really an interview question. Yeah. You can work together. That's okay. Okay, another 30 seconds maybe. At least you got some clue. Right? Give me 1 moment. Just wait for 30 seconds. And then any one of you can just contribute your answer. And then the good thing about this approach we are showing you is you can, when you have some, well, of course, you don't really prove a big program using this approach. That would be unfeasible. But I would say for simple strategy, like say we want to swap the 2 variables using just swap the x and y using just the 2 variable without any new one. You can easily use this approach to prove it formally. Okay. Okay, anybody want to contribute? You raise your hand first. Okay. Yeah.
I'm not sure if it's right.
Okay, what about you? I'll write it down exactly what you say.
So x is equal to x plus y minus x.
X plus y.
Minus x.
Okay, go ahead.
And y is equal to x plus y minus x.
But x is already updated.
Oh, right.
Yeah, right? Okay. Guys, should I? Oh, okay. Another one. I can tell you what my thought was. I could be wrong, by the way. How about I start with the first line of my solution? Okay. Okay. You want to continue from there? Okay, go ahead. Give me one line. What? Y equals y minus x. Are you sure? Why? Another one? I thought we're done, right? Are you sure? Well, why don't we try to verify that? Okay, just informally. Okay. Let's say x is simply 10 and y is 5, right? Okay. So now x would just be 15 to begin with, right? Now y would be y, which is 5, minus 15. You got minus 10. Okay, and then x would be, which is y in minus 10 plus x. In that case, it's 5. You got minus 5. Right? It doesn't seem to be. What's x? X is 5, right? Oh, 15. Sorry. 15, and then what you get is 5. X is 5, but y is now minus 10, right? Huh? You mean y is a? You mean you want one more line? Yeah. Okay, you want y is equal to y times minus 1? Like that? Okay, you got 4 lines. Y is equal to negative 1. Oh, negative y. Oh, sorry. I couldn't hear you. Yeah. Okay, that's good. Okay, that seems to be working, but now the question is, can you prove it? Can you prove it though, right? Okay, anyway, my point is, the value of this approach is, given the same post condition, you can actually justify to see different strategies of implementation if they can establish the post condition. Okay, what I would like you to do before Thursday, you want to just give us your proof by Thursday? How about I will take down your name and make sure you do it. Okay. Since you volunteer, right? Okay. So now this is your implementation here. 1, 2, 3, 4. Okay. Write it down in a legible form and then send it to me. I will send it to everybody. How about that? Okay. By Thursday before the class. Okay. Okay. Good. Okay. Okay, guys. I'll see you on Thursday.